So I continue with the subject of FPGA. So far, I just do a review first. What we talked about so far was that FPGA stands for Field Programmable Gate Array. And if I want to tell you in a simple term what it does, it's just that there is an IC that is basically flexible. That means you can program the hardware inside, okay? So what you're doing is you're programming the connections between the unit cells inside and the blocks. So what is connected to what? And every time you write a code, the construction of the circuit inside is different. The analogy would be that let's say you have a bunch of Legos inside, and then each time, according to the instruction, you can make something new. It's the same thing. You have blocks, and every time you can make a new circuit. So that's what the whole course from now on is about. So you're going to learn. So I said the codes that you can write are either Verilog or VHDL. We are going to just focus on Verilog. And if you remember from yesterday, I said actually there are only two companies that are dominating the FPGA, Xilinx, because they invented FPGA. So if you Google FPGA, lots of Xilinx boards and softwares will come up. And then their competitor, now it's Intel. So that's 90% of the market. That's where you Google the board we are using, and Quartus, we get them from Intel website, right? And we use the software to write our code, and then we connect the board to the computer and implement our design that is written by code to the circuit. So that's what we're doing. Now, the language that, so I want you to get it from the beginning that we are basically making hardware with writing a code. Okay, so we are making different hardware design. Logic circuits are inside. So yesterday I talked about what are unit cells, and you have flip-flops inside, arithmetic unit, and you have what else do you have in the beginning? So you have arithmetic unit, and you have lookup table, which is like a computer form of truth table. That means that for a combination of 1 and 0s, you have different outputs. So that's what you have inside. Okay. So what is here, the code that you're writing, it's called Hardware Description Language, or HDL. Before moving forward, don't, as I said, confuse FPGA with microcontrollers. Microcontrollers are application specific or ASICs board. FPGA are flexible. So that's one of the major differences. Yeah. You can, yes, exactly. You can. Yes, exactly. It's not flexible. That's ASICs, like application specific. But this one, no, you can make it to do, you can make it to become any circuit, not any circuit, but you can make it to act like a microcontroller too. Yes. Okay. It has its limits, but of course, any device has its limits, but it can be programmed as microcontrollers. I know that for sure. Well, yeah, yeah. I mean, you just pick up an application and you can design it. That's up to you, right? The constraints that I'm talking about is in terms of, for example, timing, and which I talk about the constraints. So the design that you are, so it should be RTL. They say it should be registered transfer level. It should be RTL. That I'll talk about later. So it has its own constraints, but I'm sure there are lots of ways that you can play with it. Some I have seen, some I have not seen, but like I guess just Googling will give you the answer, right? Just Google FPGA, what did you say, graphic card, and see if anything comes up, then it's possible. Yes. I mean, yeah, because there are millions of applications, right? I was talking about it yesterday, like automotive, defense. I can't even when you type in Google FPGA applications, millions of things will come up. So it depends on what your area of what do you want to do, and then search, right? Google is your friend, I guess, for when something is this vast and this new, actually. Yeah, you can do it now. Google and tell me if you see anything, or I can do it. How to create an FPGA graphic card. Don't quit your day job. Yeah, it is possible. Yeah. Yeah, but good question. Yeah. Okay. So so this part, as I said, it's called the program that you use, the code, is called hardware description language, because as I said, our focus is we are designing hardware at the end of the day when you work with FPGA. So that's why you hear HDL a lot, and it's called hardware description language. Okay. So if you remember from your digital class, you have different digital system modeling, right? So you have either combinational logic, which is you have like a couple of gates connected together, right? So digital systems, again, it's just a review. You remember, I don't know. So digital systems, if you remember from your digital class, can have two forms, right? So one of them is combinational logic. It's when you have a bunch of gates, inputs and outputs, and it's not basically has any and no notion of time. You don't have any notion of time. So you have inputs, and meaning there is no clock that is controlling this, right? So you have input to output, no feedback loop. That's a combinational circuit that you learn first thing in digital. Then you move on to the second kind of digital systems, which are called sequential circuits, right? Sequential circuits. So they have actually notion of times, and it has a combinational part, then it has some feedback loops. For combinational logics, the examples can be multiplexer, demultiplexer, arithmetic circuits that you have seen. They are made out of these digital logics. But sequential circuits, usually you have like a combinational circuit. If you remember, for example, how flip-flops are made, they're all made of combinational circuits, and then you use the concept of feedback. And The basic principles like flip-flops, for example, flip-flops, they are capable of holding a value, but the whole system has a notion of time, right? So that means with each clock signal, the value will change. And examples of sequential systems, if you remember again, registers, counters, shift registers. So again, we have two kind of digital systems that we can design, either combinational or sequential. Combinational logic, multiplexer, demultiplexer, no time is involved. Sequential circuits, counters, shift registers, they're moving with time, basically. You have to have a clock signal to change the value. So you can design either. Now, how can we, okay. Now, there is different ways of implementing your code, okay? So you want to tell FPGA to make a logic circuit. So you say, okay, I'm writing a code. Now, there are different ways to implement this. One of them is behavioral model. So you can use either when you code. You can say, okay, I'm using behavioral model, or you can say I'm using a structural model. So behavioral model is a high level of abstraction, basically. So you tell your system what it's supposed to do, okay? So the way you write your code, you say, okay, if I have these two input, give me this output, and if the input is this, give me that output, and then I don't know, and it with this. So you talk about behavior. You don't say necessarily connect this wire to that wire, connect that to that. You don't tell that. And when you use behavioral model, then you let the software to decide to connect what to eventually give you a circuit that matches the behavioral model that you want. Okay, so that's one way of programming. Another way of programming is a structural model. This one, that means you specifically, when you write a code, you specify connections. Again, remember, what this is all about is you're designing a hardware, right? So you can say, so at the end of the day, you want to connect the multiple blocks inside the FPGA. And so in a structural model, you get to specify the connections. Whereas behavioral model, you just let the software to decide. So you will see in future when you use a structural model, in this level, you have to instantiate modules. You can say, okay, I want like an AND gate and an OR gate, exclusive OR gate, and then wire it to another gate. Like that would be, if you write it like that, that would be a structural model. But you don't go actually to the gates. It's one abstraction level higher. So you design modules. Whereas if you want to, modules means like a combination. Whereas if you want to design, if you want to go to the gates, to the core gates, then if you want to use AND OR gates, exclusive OR, exclusive NOR, NOT gate, then that's the gate level model. And I'll show you examples of all of them when we move to the software, but you should know at least It's not just one way to write a code. Okay, it's up to you to decide what abstraction you want to go after. This is like a lower level of abstraction. So you go really low to the gates. You should be very specific in the individual connections inside logic cells, and it's I should tell you, it's similar to assembly language, right? Assembly language, it's the same thing. So I wouldn't advise this because, as you know, like you can write. The good news is that when you write a code, you can mix them. You can write some of your code in behavioral model. You can then start a structural model. You can write some of your code in gate level model. It's just like traditional programming. So they are not exclusive. So you can write your code in different levels. Okay. So, so in summary, when you write a code, you have an option to talk about behavioral model or a structural model. So you can speak, again, the analogy would be go bring me water. That would be one command or code. That's behavioral model. Then it's up to me to walk or run or I don't know, jump to the kitchen to bring you water. It's up to me, whatever works. But a structural model is like more specific. But it's like, okay, go and open the door and take 5 steps. It's like, and then open. It's like more detailed. Gate level model is really abstract. It's a lower level of abstraction. It's like assembly language. It's like all the details, even go to unit cells. If you remember cells I talked about yesterday, it goes inside the blocks. So it's better. I don't touch this. So we just do. When we start coding, I'll either mix them or just use behavioral model or a structural model. Okay. Any questions so far? No. Okay. So when I was talking about structural models, I said you can design. That's where you design modules, and you might ask, okay, what do you mean module? What does it mean exactly? So now I want to talk about modular design. So what are modules? Modules basically implement blocks of hardware. Okay, so because HDLs or hardware description languages were created to implement a modular design. They are instant. So last time I talked about an FPGA, and I said there are already pre-built building blocks inside, right? So the modules you will write are describing blocks of hardware. But by blocks of hardware, I mean like a counter, like an adder, a decoder. Um, so what you do, you instantiate hardware blocks. So modular design means that you are making like a counter, like an adder. So and they are there. So they don't change. And then once you make a module, then they don't change dynamically, right? They're the way they are. They are fixed. And like in programming, you know that you use while loops, for loops. You cannot do that with your module because you're working with hardware, right? So you don't know each time, for example, if you use a while loop, um, when you make a um, counter, for example, you can't change it like for each loop. You cannot change your module because then the hardware will change, and you don't know that you might get into, if you leave it to iteration and make your modules dynamic instead of static, somewhere it might create a problem because you're not basically monitoring your module. So what I'm trying to say is that when you create a module, make it a static. It shouldn't change. Okay? Okay, sorry. Okay. So so we are still on HDL, hardware description language. So far, you know that, okay, so I have this IC, I want to program it, and there are gates inside, and I I can either program it uh, I can work with behavioral model of the system when I write my code, or a structural model, or gate level. Now you have to first, when you start designing, first of all, of course, you should understand what system you want to produce, right? And but when you write your code, it doesn't automatically go and be implemented in the hardware, right? It has to be checked, which makes sense, right? So I talked about it yesterday again. A simulator may be used to interpret your code and predict its behavior before it goes to the hardware. And later, a synthesis tool may be used to implement the design in programmable gate array inside. Okay. Now, so what I'm trying to say is that there is a test bench module involved with FPGA. So you write that, you describe your module. You say, for example, I want the counter to do this. And then you have to test it, right? So how do you test it? You use simulators. So they execute the steps that you entered and see if it can produce the result that you want to see. Okay, so let's see an example of Verilog. I just want to expose you to what an HDL language looks like. So first of all, I was talking about module, because what you're doing, you're creating a module, right? For example, a counter, as I said, an adder, half adder. So you're creating hardware because it's a hardware design language. So keep that in mind all the time. And because of that, when you write your code, you start by the keyword module. That's why I was saying, yes, yes. If you're doing a structural model, yes. And so what are inside are like gates, flip-flops, and then last time I talked about lookup table. So those are the main ingredients of your FPGA, because like when you have a full adder, there's a full adder there, which is the basic of module of arithmetic, right? Then you can play with it to do multiplication, subtraction, division, etc. And then you have another one, you have a flip-flop, or you have a bunch of flip-flops for when you want to create sequential circuits. And then there is a lookup table, which helps you, which is the hardware version of the truth table. So all those blocks will be connected in a way to eventually create your design. Okay, so you have building blocks, as I said, like Legos. The analogy would be Lego. They are there, and every time you program, you can say put this on this, put this on that, or just say I want a house and make it, and it makes it for you. Okay, and so you're creating, as I said, modules. So let's say if I want to make, and then you connect them. Now let's say I want to create, for example, a half adder. So the keyword is, let's say I'm typing now, okay? The keyword first is module. If I go to Quartus, you see here, module. So it's the keyword that you have to use when you want to create a circuit, either sequential or combination. Now, I want to make an half adder, for example, okay? So after module, so guys, what I'm talking about is like a basic form of how to write a Verilog code. So it's a very simple form. So these are the syntaxes. You have to write module, and then you have to give your module a name. So you choose the name. You choose the name. So I say, for example, half adder, because it's a half adder. It should make sense, of course. Half adder, okay? And then parentheses. Here it looks like a function, I guess, in other languages. So you should put, instead of, so if you remember, for example, in C, C++, or MATLAB, when you create a function, in parentheses, you put inputs and outputs, right? It's the same thing here, whereas the inputs and outputs are the inputs and outputs of your design, okay? So now half adder, again, if you remember, I'm going to just Google half adder to show you the circuit. Here. So this is a picture of a half adder. This is half adder and full adder. This is an half adder, right? So what do I have? I have two inputs, two outputs. So in functions in C++ or MATLAB, again, you had inputs and outputs in the parentheses. Now it's the same thing. The difference is that I'm talking about hardware, right? I'm talking about the inputs that goes to my hardware design. Let's say I'm designing this, and whatever is coming out. So my inputs are A and B. So when I come and type, after parentheses, you have to give it input, and you use the keyword input, and it Verilog will understand what you're talking about. So you say input, and then you give it a letter A. Then you say input B, and what are the outputs? The outputs are S and C. So you can say output, and the way I'm writing it is actually, it's very it's a conventional way. It's not that I don't have any space here, but usually it's written like this, actually. next line, next line, next line. It's a convention. So output C, comma, output S. And then you close it, and then you have to put semicolon. Whereas in C++ and MATLAB, you don't need semicolon after your first initiating. And then in Python, you need colon. So it can get confusing. In each language, the syntaxes are, although the core is the same, but these small things can throw you off. But remember, for a Verilog, you need to finish it with semicolon. Okay, so again here, this is another one, but you can type here module half adder and then in the parentheses, and then you have a semicolon at the end. Okay, so that's how you start making a module. And then you go on and what you have is, again, you go and look, you have an OR gate, an AND gate, and exclusive OR gate. So what you do, you say, okay, I have XOR, I have two inputs A and B, and my output is S. So if you type XOR, it will understand. So you say XOR, and then you put your output first, always. So you say S, A, B. Why? Because S is my output, A and B are my inputs. S is my output, A and B are my inputs. So A, B, S, exclusive OR, S output, A and B inputs. Okay? And then, what about the next one? You have an AND gate. A and B are inputs, C is output. So you say AND C, A and B. That's it. So you type it, when I get here, you type all of it here, and then once you're done, you should end it with the keyword end module. Okay, so this is just to expose you to Verilog. Now again, this first you have to create a module. Then it comes with a name. Put your inputs and outputs, and go see what are the basic modules in your circuit. And these keywords are already known to Verilog. So you type this, and once you're done, you have to finish it up with end module. Now, every line, like exactly like MATLAB or C++, you finish each line with semicolon. Okay. So you are adding an addition of one bit number with another bit. That's it. Okay. So as you see, the syntax is somewhat similar to C++, more or less. And I think it's very similar to functions in C. And it's just that you put, instead of parameters list, now you have part list. Yeah, because again, you're designing a hardware module. So another thing that you should remember is that you start with outputs for your small modules. Okay. So the first input, the first element specifies your output. The remainings are inputs. Okay. Now, so now you know how to basically declare a module, right? So it consists of the module keyword and a part list. Okay. Now, how about like a 4-bit adder? So it will be, what I'm trying to say is that here you have one input. How about when I have like for example, 4 A's and 4 B's. So now let me start with a 4-bit adder. So what do I mean by 4-bit adder? So you have number A that has 4 bits, okay? And then you have another number B, it has 4 bits, 4, okay? So you add them. You want to create a circuit that adds them. So the output, let's say S, is a 4-bit number, which contains the result of the addition. And then it might have a carryout, right? Because when you add, you don't necessarily get 4 digits. You sometimes have C out, if you remember from your digital class. So you have S and then you have C out. Okay. So what about here? How would I write a code for something like this? Now, one way of doing this is I want to introduce you to a keyword that you see in Verilog a lot. It's REG, and it's short for registers. Why I want to talk about it here for this example, because the outputs they are treated as registers because because they can hold the addition of 2 numbers. And when you want to write or represent S and C out, you can, the one way to do it just to define them as REG or registers. Registers are basically, if I want to say it simply, are the storage, data storage units. As you know, I guess from your digitals, you have seen registers before. That's where the name comes from. So registers in Verilog are data storage units. And for with the word, the syntax is REG. So they can hold a value that is assigned to them. Oh, okay. So if I want to write a code for this, I'm going to say, okay, first I have to use for the 4 adder. I'm going to use the keyword module. You know that by now. Then you know that, okay, after module, I have to put a name for my module, which should make sense. I mean, Verilog doesn't care, but for you, usually when you write a code, the name should make sense. So let's call it 4-bit adder. And then we go to inputs. So inputs was a 4, so I have 4 bits A, okay? So you can say input, which is the keyword that I used before, okay? And now because you have 4 bits, the way to represent it is 3, go to 0. Again, you have seen this before, especially in MATLAB, 0, 1, 2, 3. So that means you have 0, 1, 2, 3. You have 4 bits. So I want to tell Verilog I have 4 bits in A. So you say input 3 to 0 A. You define it like this. And again, input. So what I'm trying to do is just to expose you to Verilog. Don't get scared. We are going to type them out later and get the output. So for now, just let your eyes to be familiar with the syntaxes, okay? And then again for B, I have 4 bits. So it goes from 3 to 0, that will be your B. Again, semicolon, semicolon. And then you have to define your output. Again, your output can have, I mean, if you remember, I said there are 2 outputs. One is your S, and then you can have a carry. So the one way to define that is you type output, and then now you are using a data unit to storage your output, right? So you have to use the keyword reg or register. So you say output is reg and go from 2 to 0. One of them is S, and C out is just C out. I don't have any space, so I go to the next line. So you say output and it's register, and you say it's C out, and then you write your code. I mean, you connect the modules to make a 4-bit adder and then end module. Okay, so that's basically Verilog Primer for you. So you have modules, you have declaration, and then you specify input and output. And as I said earlier, it's then here when you write your code, you either talk about the behavioral model of the circuit you want to do, or you talk about the connections. Okay. So here, just notice that 2 outputs are defined as registers with reg, basically keyword. Okay, because there are 2 kinds, because you're working with hardware, right? That's why. There are 2 types of signal identifiers. It's either wire or registers. Okay, the difference between wire and registers, so I'm going to write it because it's important. So there are 2 types of signal identifiers. Wires and registers. Okay, so wire is actually a keyword. So you just type wire, and register you type reg. So again, the good news is that the name represent what exactly they do, because wires, they implement the connections between elements, and registers are holding values. So if you want to hold a value, you type register. If you want to make connections, you type wire. So the important difference between wire and registers is that wires are passive, right? Registers are active. That means that they're capable of driving a line, whereas wires, they're just transferring. They just take the value from the drivers they are connected to. They don't have anything inside of them. They're just passing information, whereas registers are basically active. So they provide the data. Okay. So if you want to declare, for example, 3 wires, the way to do it in Verilog, you type wire, and then you say X, Y, and Z, semicolon. So it's if you do this, you're declaring 3 wires. And for example, if you want to declare three registers, you say reg A, B, C. And then let's say you have created a module to do something. Okay, so I can say my circuit, for example. You can name it, and then my output can be a wire, actually. Okay, so the output can be a wire, and the input can be registers. That means take the information of A and B to the Z. For example, for an OR gate, you can take A and B to Z. So by now you have to at least have an idea of what wire is and what REG is when you see a when you see a Verilog code. Okay. For example, if I have a circuit like this, like I have inputs X and Y, and then goes to, for example, an AND gate and goes to A, okay, and you want to connect it to something, then you can define your X and Y as your input and A as your output. And you can, and if you have already values here, you can say, instead of saying input, you can say register X and Y, and then wire A if you want to connect it to something else. Stuff like that, okay, that you will see later. So for now, don't worry about it. Just at least know what reg is. Registers, wires are just connections. And another thing I want you to know is that when you create a module type module, give it a name, specify the input, output, and end it with the keyword end module. So yeah. So any questions so far? Is it too much information, or you're good? Okay. Okay. I'm almost done. But yeah, I don't want you to get scared, because at the end of the day, if you know what behavioral basically abstraction is when you write a code, what is a structural model, and I just gave you like a basic Verilog so that at least you're exposed to it, you'll be fine, at least for the labs that we'll do in very near future. Okay. So all the elements that you designed by Verilog, they are all so let's say you want to, they're all concurrent by default. What does it mean? That means when you want to define, for example, a sequential circuit, okay, you can let me talk about control statement first. Remember how you had like if in programming in C++ or MATLAB? So you can have the same thing in Verilog, control statement. meaning that so they're supported in Verilog, which is pretty cool. It's exactly like MATLAB and C. So you can have actually if a function. So, but when you use it, you should have like begin and end. So when you look at the code, you will see something like this. For example, you see begin. For example, this is like a simple code. You say begin, put, for example, register B in A. Okay, but if A is 0, there's nothing in A, and then put 0 into C. You see how cool is that? It's exactly like other programming languages. You put something from here to here, but the difference is that here now you're working with hardware. So you're saying put the whatever you have in register B into register A. If there's nothing in register A, then put 0 in register C. And then again, you have if, not only you have if, you can use else in Verilog. So you say else, for example, put 1 into B, right? You're working with 1 and zeros, right? It's digital design. So you either have 0 or 1, and then you can end it. So I think it's amazing that you have conditions even in Verilog, exactly like other languages. But here you are using zeros and one. And the other similarity is equal, equal. If you remember in all the programming languages that you have seen before, equal, equal means equal. And only one equal means whatever you have here, put it here, right? So that's the standard common knowledge for any programming language that I'm sure you have seen and know. It's the same thing in Verilog. So know that you can control. You have control statements in Verilog. You can use if and else. Now I'm going to finish with another keyword, which is always. So there is a keyword that is kind of while in other languages you see while this is true, do that. In Verilog, it's always. For example, you can, and the syntax is kind of odd. So you type always, and then you have at sign, something like this, and then you put your condition inside. Okay. For example, again, I don't want you to think about numbers. You're working with hardware, right? And 1 and 0. So you can say, for example, you can say when a condition is met, okay, remember while, so you say while this condition is met, it's the same thing. You can say always or as long as the condition is met, do something. So for example, you want to, when you have positive edge in your clock signal. And actually there's a keyword for that. It's called POS, POS edge. So if you type always at pause edge, that means as long as there is a positive edge, as long as that's true, okay, or while that's true, do something, for example. Every time this condition is met, use this register C, for example, okay? Yeah, I'm going to end it here.